AB Calc section 2.1, the idea of limits. Our essential learnings for today are really comparing two different types of rates of change. We've got average rate of change, which is the slope of a secant line on a certain interval. And we've got instantaneous rate of change, which is the slope of a tangent line on a certain interval. And what happens to a secant line as 2 points on a curve get very close together. So for example, I want to draw a secant line from x on the interval from x equals 1 to x equals 3. This dotted red line, or excuse me, blue line, is going to represent the slope of a secant line, which would be f of 3 minus f of 1 over 3 minus 1 in this case. Now, the slope of a tangent line is a little bit harder to work with regards to the actual equation for slope, but a slope of a tangent line is a line that is tangent to the curve at that point. So this would be the slope of the tangent line, which of course you can imagine is going to be difficult to calculate using traditional methods, seeing that we would be dividing by 0. So those are the two topics specifically that we're going to analyze today with regards to functions and average rates of change as well as instantaneous rates of change. So let's get started. So a secant line, as it says here, connects two distinct points on a curve. So we're going to find the slope of the secant line between the points 1, 1, and 3, 9. Well, we just about did that. We set it up. We took y2 minus y1 over x2 minus x1, which was 9 minus 1 over 3 minus 2, which is 8 over 2, which gives us 4. So the slope of the secant line that I drew up there in blue would be 4. So on the interval, let's say on the interval from 1 to 3, the slope of the secant line is 4. Okay, now let's do the same thing, but let's bring that second point or second coordinate closer to 1. So we're going to bring it from 3, 9 back to 2, 4. So the slope of this secant line on the interval from 1 to 2 will be f of 2 minus f of 1 over 2 minus 1, which will be 4 minus 1 over 2 minus 1. So on the interval from 1 to 2, the slope of the secant line for x squared will be 3 over 1, which is 3. Okay, let's do it again. Let's bring that point even closer. So now we're going to utilize the points 1, 1 and 1.5, 2.25. So the slope of the secant line on the interval from 1 to 1.5 will equal f of 1.5, which is 2.25, minus f of 1, which is 1, over 1.5 minus 1, which will equal 1 1/4 over a half. So on the interval from 1 to 1.5, the slope of the secant line will equal, 2.5. When you divide by a half, it's the same as multiplying by 2. So if I were to look at this with regards to the graph of x squared, my first secant line, of course, was from 1 out to 3, and the secant line looked like that. And then my second secant line was from 1 to 2, and it looked like that. And my third secant line was from 1 to 1.5, and harder to see, but it would look kind of like that. So you can see that the slope of the secant lines are starting to approach the slope of the tangent line at x equals 1. We're going to talk about that on the coming slides. So in general, the slope of any secant line can be calculated using slope, y2 minus y1 over x2 minus x1, where x1, y1, and x2, y2 are two distinct points in the curve. So an application of slope typically It has to do with speed or velocity, right? So suppose you want to calculate your average velocity as you travel along a straight highway. If you pass the milepost 100 at noon and the milepost 130 at 12:30, you've traveled 30 miles in 30 minutes. So your average rate of change on that interval would be 30 over 0.5, which is 60 miles an hour. Okay, so we're going to see that coming up in future lessons and chapters. That's not going to go away. So get used to the idea of speed and acceleration and all that good stuff. Okay, so moving on, the secant lines from part A through C in example 1 are starting to approach a single line, the one we drew in yellow, when x equals 1. This single line is called a tangent line. It's the instantaneous rate of change, okay? If we try to calculate the slope, like we said earlier, using traditional methods, we run into a problem because we have a horizontal change of 0. This means the denominator would be 0, so we got issues mathematically. We can, however, represent the slope of a tangent line when x equals 1 for f of x equals x squared as the following. Okay, so the slope of a tangent line is going to be the limit as x approaches 1 of the slope of the secant line. So here is the slope of the secant line, f of x minus f of 1 over x minus 1. All right, we are going to take the limit as x approaches 1. This is a topic from pre-calc where the notation should not look foreign to you. Okay, so in general, for any point x1, y1, for the function y equals f of x, the slope of the tangent line is equal to the limit as x2 approaches x1 of the slope of the secant line. It looks just like this. Okay, in one other form, which I'd like to look at, if I took the limit as x plus h approaches x of our difference quotient, that is a third representation for this slope of the tangent line. Now, if I look at this portion in yellow here, if x plus h approaches x, that's really like h is approaching 0. Okay, so it can be written either way. All right, so let's look at the next example. But first, the slope of the tangent line, as we've mentioned a number of times prior, is called the instantaneous slope at a specific x value. So let's now, we're going to calculate the instantaneous slope of the function f of x equals x squared when x equals 1. So we're getting to what we want, right? We had the slope on the interval from 1 to 3 of the tangent, or excuse me, of the secant line was 4. Then we had the slope from 1 to 2 of the secant line was 3. And then we had, I don't remember the color I used, maybe green, I don't remember, from 1 to 1.5 was 2.5. So what is happening to this second value? Well, it's approaching 1, right? Or h, right, the distance in between is approaching 0. So the first thing I'm going to do is I'm going to simplify the difference quotient for f of x equals x squared. So first, I like to do this. This is just preference. F of x equals x squared. F of x plus h is x plus h quantity squared. I like to do this and lay it out first so I don't goof up the algebra. 2x plus h squared. So f of x plus h minus f of x over h is equal to, that would be x squared plus 2xh plus h squared minus, we've done this in previous chapters, f of x, which is x squared, all over h. As I combine like terms, you'll see the x squareds reduce. And I'm going to factor out an h from what is left over. So that'll leave 2x plus h in the numerator times h, and h in the denominator. So we'll see that the h's reduce. Therefore, the difference quotient is equivalent to 2x plus h. So f of x plus h, or I guess I should specifically call this x plus h squared minus x squared over h, which is the difference quotient for f of x equals x squared, reduces to this. Okay, so now if I wanted the instantaneous rate of change, so the slope of the tangent line, I would take the limit as h approaches 0, right? We said, or as x plus h approaches x. So as h approaches 0 of 2x plus h. Let's look at what that will do for us on the next slide. Okay, so we are going to use the simplified difference quotient, which is what we came up with over here. So the slope of the tangent line is the limit as h approaches 0 of the simplified difference quotient. Now the difference quotient without the limit is the slope of the secant line. All right, but as h approaches 0, then we are considering it a tangent line. So what we're going to do is we're going to substitute a 1 in for x, right? We wanted to know the slope of the tangent line when x equaled 1, and we're going to substitute a 0 in for h. So the slope of the tangent line at x equals 1 is going to equal, now with regards to limits, I'm going to plug a 0 in for h, and in doing so, the operator, this operator right here, disappears. So I'm plugging in a 0 for h, I'm plugging in a 1 for x. So I get 2 times 1 plus 0. So the slope of the tangent line when x equals 1 is equal to 2. So we saw, I'm not going to go through all the formalities, but we saw a slope of 4. Then we saw a slope of 3. Then we saw a slope of 2.5. And now at the point x equals 1, we see a slope of 2. So it makes sense, right? As you look at the graph, this is the idea of limits, you guys. So at x equals 1, I might change this to a different color. Let's go 2. I've got a slope of 1 exactly, right? That's the instantaneous rate of change at x equals 1. At x equals 1.5, I had this decent approximation, right? That was a slope of 2.5. At x equals 3, x equals 2, I had a pretty good approximation of the slope of the tangent line. And then x equals 3, I had the worst of my approximations. So you can see that those slopes are approaching the slope of the tangent line. Does this make sense? Yeah, sure it does. So we're looking at that third part here. And it does. It makes sense that the slopes would approach the slope at, the slopes of the secant lines approach the slope at the tangent line when x equals 1. Okay, let's look at a second example here. Actually, I guess this is example 1. I'm going to simplify the difference quotient in the other form, f of x minus f of a over x minus a, using the function 1 over x. So f of x minus f of a, f of x minus f of a over x minus a, it's going to be equivalent to 1 over x minus 1 over a over x minus a. All right, now I'm going to do a method called clear fractions. I'm going to multiply by ax on top and bottom. Multiplying by ax is the same as multiplying by 1. I'm allowed to do that, but in the process, what I'm going to do is I'm going to clear out the fractions in the numerator. So the denominator, I'm not going to change yet. I'm going to have ax, x minus a. In the numerator, when I distribute, I get a minus x. Now, that may seem like it's fully simplified. It's not. I'm going to factor out a negative 1 in the numerator. It's going to give me x minus a, and you'll see clearly I've got a little extra that I can work with and clean this up. So I'm going to reduce out the x minus a, which gives me f of x minus f of a over x minus a simplifies to negative 1 over ax. So this expression represents the slope of a secant line from a to x. From a to x, the slope of the secant line is equal to negative 1 over ax. All right, so let's do a little work here. Parts A and B look like they're secant line slopes. So from 1/2 to 1, the slope of the secant line, I can do a direct substitution, okay, of negative 1 over ax. Well, negative 1 over ax would be a is 1/2, x is 1. So the slope of the secant line from 1/2 to 1 is going to be -2. Okay, -1 over 1/2 is -2. Now the slope of the secant line from 3/4 to 1, same formula. This is just a formula for the slope of the secant line, will be 3/4 times 1 in the denominator. So the slope of the secant line from 3/4 to 1 will equal, looks like -4/3. All right, so how do we find the instantaneous rate of change in this form, right? This is not as h goes to 0 because, well, we're not dealing with the difference quotient in the first form. So how would we find the slope of the tangent line? Well, the slope of the tangent line, okay, on the interval from a to x, at x equals a, will be equivalent to the limit as x approaches a of our difference quotient. So in the case of our function at x equals 1, okay, that's our a value, we would find the slope of the tangent line by taking the limit as x approaches 1 of -1 over ax. Well, I know that a equals 1. I'm given that. And I want to know where what the slope is at when x equals 1. Therefore, I'm going to do a direct substitution here. All right, so I got -1 over 1. And this one is the one I am subbing in right here. All right, so it looks like the slope of the tangent line at x equals 1 is going to be equal to -1. Let's see each of these take place. So here's the function 1 over x, approximately, with vertical asymptote at x equals 0, horizontal asymptote at y equals 0. Okay, and here is 1/2, here is 3/4, and here is 1. Okay, so if I do, let's say, the slope of the secant line from 1/2 to 1, I'm being told based on my calculations that that slope is -2. Okay, so the slope of that is -2. And then the slope from 3/4 to 1 on this function is -4/3. Okay, so -4/3, that looks reasonable, even though my sketch isn't to scale. And then the slope of the tangent line at x equals 1, I'm being told, at least based on my calculations, is -1. And it is. And you guys, it makes sense, right, that the slopes would be approaching in the pattern that they are, and that is how you'd find the slope of the tangent line on the function 1 over x. Okay, let's keep going. We've got a couple more slides. We're just going to do a couple practical exercises with it. Okay, example 2, find the average rate of change. Okay, average rate of change should immediately tell you that you are going to find the slope of a secant line. And the slope of a secant line, I typically always default to the second form. So the slope of the secant line here would be f of x minus f of a over x minus a. And I'm going to call a 0 and x 2. Okay, so this is going to be f of 2 minus f of 0 over 2 minus 0. So f of 2, we got to do a calculation. F of 0, we have to do almost no calculation. I plug a 0 into that function, I'm getting 0. So what if I plug a 2 in there? I'd get 2/3, 2 to the 3/2. So 2 to the 3/2 is the same as 2 cubed, and then taking the square root of that. So that would be 2/3. The square root of 2 cubed would be the square root of 8. Okay, now I don't see an answer that has a square root of 8 in it. So I'm going to simplify this slightly to 2/3 square root of 4 square root of 2. So I see the square root of 2 that I'm looking for, which shows up in most of these answers, which would be 2/3 times 2 times the square root of 2. Okay, so f of 2 is equal to 4 over 3 root 2. So I'm going to put that into my equation here for the average rate of change. So 4 over 3 root 2 minus 0, which I'll just leave as 0, or not there at all, divided by 2. And when I divide by 2, the 4 reduces, giving me 2/3 root 2. So it looks like our answer here is C. All right, let's move on. Example 3. What is the instantaneous rate of change of f of x equals x at x equals 5? Okay, a couple different ways to do this. One is analytically. So analytically will mean we'll actually find the difference quotient simplified. So let's find f of x. Well, we know what it is. It's x. And f of x plus h, well, that would be x plus h. So f of x plus h minus f of x over h, what would that be? Well, that would be x plus h minus x, which is just going to be h over h, which is 1. So the difference quotient simplifies to 1. So what would happen as I took the limit as h goes to 0 of 1? Right, this is going to be the slope of the tangent line. Well, there is no h. This function's slope is not dependent on h at all. What that means is that the slope of the function is always 1. Would that make sense? Well, what's the slope of a line? Y equals x. It's always 1. Okay, so our slope of the tangent line when x equals 5 is 1. But graphically, how would we see that? Well, here's the equation, or here's the coordinate grid. Here's our function, y equals x. What would be the instantaneous rate of change when x equals 5? Well, what's the slope right there, right? What is the slope there? Well, it's the same as the slope everywhere else. So the slope, you can see that the slope of the tangent line when x equals 5 would be 1. Okay, let's look at a word problem from back in the old days of, wow, the early days of the 2000s, back when most of you were, taking honors geometry. Okay, so rocket A has positive velocity after being launched upward from an initial height of 0 feet at time t equals 0 seconds. The velocity of the rocket is recorded for selected values of t over the interval from 0 to 80 seconds, as shown in the table. Find the average acceleration of the rocket over the time interval 0 to 80, indicate units of measure. Okay, so hint, hint, we're working with average rate of change, and the rate of change of velocity is acceleration. So what that means is the change in velocity over the change in time is equal to the average acceleration. I almost put rate, but whatever. So the average acceleration is the change in velocity over the change in time. So on the interval from 0 to 80, the average acceleration will equal the velocity at 80 seconds minus the velocity at 0 seconds over 80 minus 0. So that's change in velocity over change in time. Let's see what that ends up being. Velocity at 80 seconds is 49 feet per second. Velocity at the start, 5 feet per second. Over the course of 80 seconds, that's 44 feet per second over 80 seconds. I believe that reduces to 11 over 20, and that's feet per second per second. So that's feet per second squared. All right, I think we've got one more example. Let's move on. All right, here I've got this piecewise function of lines, and I want to find the average rate of change of f of x on the interval from -4 to 0. So I am going to find the slope of the secant line from the output at -4 to the output at x equals 0. I want to find the slope of this dotted line right here. So the average rate of change of change will equal f at 0 minus f at negative 4 over 0 minus a negative 4. Again, if you want to, you could do f of negative 4 minus f of 0 as long as you divided it by negative 4 minus 0. Okay, so f of 0 is negative 2. F of negative 4 is 0. 0 minus a negative 4 is 4. So it looks like the average rate of change on that interval is negative 1/2 based on, just kind of how it looks. That looks accurate. All right, guys, that's it for 2.1. See you in the next video.